Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I hope you all will be fine. In the last lecture, we have seen the concept of induced EMF and torque in the single rotating loop in DC machines. In this lecture, we are going to solve a numerical related to induced EMF and torque produced in the single rotating loop between curved pole faces. So this numerical has a lot of parts in it. We will solve each part one by one here. So let us see what is the numerical now. So it is told that a figure shows a simple rotating loop. Here, as you can see in the figure, a simple rotating loop is given between curved pole faces. This is the north pole and this is the south pole. Both poles are curved, as you can see in this figure. Connected to a battery and a resistor through a switch. As you can see in this figure, the loop is connected to a battery and a resistor through a switch. This is the switch and this is the resistor. The loop is connected to a battery through the commutator segments and brushes as well. The resistance shown models the total resistance of the battery and wire in the machine. The physical dimensions and characteristics of these machines are: the radius of this machine is given as R is equal to 0.5 meter. That is the distance from the center is called the radius. The value of the radius is given here. R is equal to 0.5 meter. And as you can see in the figure, the length of the conductor is given by L is equal to 1 meter. This is the length of the conductor AB or CD. And the total resistance of the battery and the wire resistance in the machine is given here. R is equal to 0.3 ohm. And the value of the magnetic flux density is given by B is equal to 0.25 Tesla. And the battery voltage is given here. VB is equal to 120 volt. So first, what they have asked: what happens when the switch is closed? Part A. In part A, they have asked what happens when the switch is closed. When the switch in the figure is closed, when this switch will close, a current will flow in the loop, and the direction of the current across the segment CD will be inward, and the direction of the current across the segment BA will be outward. As we know, current always flow from high potential to low potential. And as you can see in this figure, positive means high potential and negative point means low potential. Since the loop is initially stationary, therefore at the start the value of the induced voltage will be 0. That is, E induced is equal to 0 at the start, because at the start the loop is stationary. In case of stationary, there will be no voltage will produce. Therefore, the value of the induced voltage will be 0. According to KVL, or by applying KVL in this loop, we get Vp minus IR minus E induced is equal to 0. Therefore, I is equal to Vp minus E induced over R. At the start, the value of the induced voltage is 0. Putting the value of E induced in this equation, we get I is equal to Vp over R. Therefore, the current will be given by I is equal to Vp over R at the start. At the start, this current flows through the rotor loop. As you can see in this figure, this current I is equal to Vp over R at the start will flow through the rotor loop. Due to this current, produce a torque. As we know, when a current carrying conductor is placed in the magnetic field, a force will be produced. Due to this force, torque will be induced in the machine. The direction of the induced torque across the segment CD will be counterclockwise. As we know, the direction of the force across the segment or conductor CD will be downward according to Fleming's right-hand rule. Across the conductor CD, the direction of the current is inward. Middle finger will place inward, and the direction of the magnetic field is towards right. And middle finger will present the direction of the magnetic field. Index finger will present the direction of current, and thumb will show the direction of the force. By applying the Fleming right-hand rule, the direction of the force across the conductors or segment CD is counterclockwise. Therefore, the direction of the current and direction of the induced torque will be counterclockwise as well. That is, torque induced is equal to 2 over pi flux into I, and the direction of the torque induced will be counterclockwise according to Fleming right-hand rule. This induced torque produces an angular acceleration in a counterclockwise direction or anti-clockwise. So the rotor of the machine begins to turn. When torque will produce in the machine, the rotor will start to move or turn. But as the rotor begins to turn, an induced voltage is produced in the machine according to Faraday's law of electromagnetic induction. When the conductor moves through a magnetic field, voltage will produce across the conductor according to Faraday's law of electromagnetic induction. The value of the voltage is given by E induce is equal to 2 over pi flux into omega. As we know, the relationship between current and induced voltage is inverse. So, when the voltage will produce in the machine, so current I falls. As the current falls, as we know, the relationship between current and torque induced are directly proportional. Due to decrease in current, torque induced will increase as well, and the machines winds up in steady state with torque induced is equal to 0, and the battery voltage VB will be equal to E induced. This is the same sort of starting behavior seen earlier in the linear DC machine. So first part is easy, and the second part is what is the machine maximum starting current and what is its steady state angular velocity at no load. As we know, I is equal to VB minus E induced over R. In case of starting current, in case of starting, as we know, the value of the induced voltage will be 0. At the start, the value of the induced voltage will be 0. Therefore, I is equal to VB minus 0 over R. Putting the value of VB and R in this equation, we get the value of VB is 120 volt and the value of R is 0.3 ohm. By solving this, we get I is equal to 400 amperes. And next question is what is its steady state angular velocity at no load? That is, what is the value of angular velocity omega at no load? As we know, in case of no load, VB is equal to E induced is equal to 120 volt. Therefore, VB is equal to E induced is equal to 2 over pi flux into omega. The value of omega is equal to VB over 2 over pi into flux is equal to VB over, as we know, 2 over pi flux is equal to 2RLB. As we know, area of the single loop is A is equal to pi RL, and the value of RL is equal to AP over pi, and the value of the flux is equal to BA. By putting the value of flux is equal to BA in this equation, we get VB over 2 pi over pi into B into A, and putting the value of A in this equation, we get VB over 2RL into B. Now, putting the value of VB R, L and B, in this equation we get omega is equal to 120 over 120 volt over 2, and the value of the R is 0.5 meter, and the value of L is 1 meter. The value of the flux density B is 0.25 Tesla. By solving this, we get omega is equal to 480 radian per second. Now we will solve part C. The part C is, suppose a load is attached to the loop and the resulting load torque is 10 Newton meter. Due to load, the torque is tau is equal to 10 Newton meter. What would the new steady state speed be? That is, what is the value of omega when the 10 Newton meter torque will apply? How much power is supplied to the shaft of the machine? The power across the shaft of the machine P is equal to what? And the power across, and how much power is being supplied by the battery? Power due to shaft, and what is the power due to battery? Is this machine a motor or a generator? As we know, when load torque will apply, the speed of the machine, the speed of the rotor will decrease. As the speed of the rotor will decrease, induced voltage will decrease as well, and due to this, current will increase. As we know, tau induced is equal to 2 R L d I is equal to 2 over pi flux into I. The value of the I is equal to tau induced over 2 over pi into flux is equal to tau induced over 2R L into B. Putting the value of torque, induced, radius, length and magnetic flux density in this equation, we get I is equal to 10 Newton meter over 2 into 0.5 meter into 1 meter, and the value of B is 0.25 Tesla. By solving this, we get I is equal to 40 ampere. By Kirchhoff's voltage law, E induced is equal to VB minus IR. Therefore, E induced is equal to 120 minus the value of I is 40 ampere and the value of the R is 0.3. By solving this, we get E induced is equal to 108 volt. As we know, E induced is equal to 2 over pi flux into omega is equal to 2 R L B omega. the value of the angular speed or steady speed is now omega is equal to E induced over 2RLB. Putting the value of E induced, radius, length and magnetic flux density in this equation, we get omega is equal to, here the value of the E induced is now 108 volt, to the value of R is 0.5 meter and value of the L is 1 meter and the value of magnetic flux density is 0.25 Tesla. By solving this, we get omega is equal to 432 radian per second. The value of the angular speed is now 432 radian per second. At no load, the value of the angular speed was 480 radian per second, as we calculate in the part B. Now, the power supply to the shaft is, as we know, P is equal to tau omega. The power across the shaft, as we know, the torque across the shaft is 10 Newton meter and the angular velocity across the shaft is, due to 10 Newton meter torque load, is 432 radian per second. Multiplying by 10 into 432, the answer is 4320 watt. Now the power out of the battery is, this is the power across the shaft. Now the power across the battery is B is equal to Vp into I. Putting the value of V and I in this equation, we get 120 into I 40 is equal to 4800 watt. This machine is operating as a motor, converting electrical power to mechanical power. Now we will solve the part D. The part D is, suppose the machine is again unloaded and a torque of 7.5 Newton meter is applied to the shaft in the direction of rotation. Now the value of the torque applied to the shaft in the direction of rotation is given here, 7.5 Newton meter. What is the new steady state speed? When the torque applied to the direction of the motion, what is the new steady state speed? And that is, what is the value of the omega or angular velocity V? Is this machine now a motor or a generator? As we know, when we apply the torque in the direction of the motion, the speed of the angular velocity of the machine or the rotor will increase. As we know, the relationship between angular velocity and induced voltage is directly proportional. Due to angular velocity, induced voltage will increase and exceeds the battery voltage. So the current flows out of the top of the bar and into the battery. This machine is now a generator. This current causes a induced torque opposite to the direction of motion. The current in the rotor will be, as we know, tau induced is equal to 2 over pi flux into omega is equal to 2 RILB. and the value of I is equal to torque induced over 2RLB. Putting the value of torque induced RL and B in this equation, we get the value of torque induced is 7.5 Newton meter. The value of R is 0.5 meter. The value of L is 1 meter, and the value of magnetic flux density is 0.25 Tesla. By solving this, we get I is equal to 30 ampere. By applying the KVL, we get E induced is equal to VB plus IR, because the direction of the current is reversed now. Therefore, E induced is equal to VB plus IR. Putting the value of VB and IR in this equation, we get the induced voltage is now 129 volt. That is greater than the battery volt. The battery voltage is 120 volt and the voltage induced is now 129 volt. If the induced voltage is greater than the battery voltage, then the machine is generated. Therefore, the angular velocity of this machine is now omega is equal to E induced over 2 over pi into flux is equal to E induced over 2RLB. Putting the value of E induced, radius, length and B, we get omega is equal to the value of E induced is now 129 volt, value of R is 0.5, value of L is 1 and the value of B is 0.25. By solving this, we get omega is equal to 516 radian per second. Now, as you can see here, the angular velocity of the machine now increase. At no load, the angular velocity was 482 radian per second. When the load torque was applied in part C, the angular velocity was 432 radian per second. When the torque applied in the direction of the motion, the angular velocity is now 516 radian per second. The last part of this numerical is, suppose the machine is running unloaded. That is, in case of no load, what would the final steady state speed of the rotor be if the flux density was reduced to 0.2 Tesla? If the magnetic flux density was reduced to 0.2 Tesla instead of 0.25 Tesla, what would be the final steady state speed of the rotor B? That is, what is the value of the angular velocity omega? As we know, in case of no load, omega is equal to VB over VB is equal to E induced over 2RLB. Putting the value of VB, RL and B in this equation, we get omega is equal to 120 over 2, the value of R is 0.5, the value of L is 1 and the value of magnetic flux density is now 0.2. By solving this, we get omega is equal to 600 radian per second. As we can see in this formula, the relationship between B and omega is inverse. If we decrease the value of B, then the value of angular velocity will increase. Therefore, now the value of the angular velocity is now 600 radian per second. Notice that when the flux in the machine is decreased, its speed increases. This is the same behavior seen in the linear machine and the same way that real DC motors behave. That's it. In the next lecture, we will discuss the concept of commutation in a simple 4-loop 2-pole DC machine.